This is a tutorial on titration curves. If you're fuzzy on your acid-base chemistry, I would go back and look at my tutorials on acid bases and buffer solutions and pH of salt solutions before doing this one, because this will require that information. And I'll assume you've already watched the previous videos. So let's take a look at acid-base indicators, because they can indicate when a titration is over. Now the point of the titration, where we've added chemically equivalent, according to the stoichiometry of the reaction, amounts of acid and base, we call that the equivalence point. That's totally determined by the stoichiometry of the reaction. Now, depending on which indicator you use, that indicator is going to change color, and we call that the end point. Now if those two aren't at the same spot, that's going to create some error. That amount of error is built into the experiment, and we call that the titration error. But you obviously want that end point and equivalence point to be as close to the same spot as you can, because that will give you the best result. A symbolic representation of a generic indicator as it reaches the endpoint would be treating the indicator as if it were a weak acid, which many are. And so you got hydrogen on the indicator, anion, on one side in equilibrium with the indicator anion and H+. What makes it a good indicator is that it changes color. For example, the indicator with the hydrogen attached on the left hand side of the reaction would be color 1, where on the other side it would be color 2, and so when it goes from color 1 to color 2, we know that the titration's over and we stop adding stuff. The equilibrium constant could be expressed like any other equilibrium constant, and you would have a Ka, and that will help you determine when the indicator would change color. We got that H plus the indicator anion concentrations on the top and the weak acid indicator on the bottom. Here are some common indicators and their color and what range. The middle column, the pH range, tells you over what color the color change happens. So color in the acidic range in the left-hand column. In the middle column, you've got pH range where that color change happens, and color in the basic range is the right-hand column. So if we take methyl violet, below pH 0 it's going to be yellow, and the 0 to 2 range is going to change purple by pH of 2. Methyl orange is going to be pink in an acidic range, and it's going to be yellow in a more alkaline range than 4.4. You kind of look for the end point to happen at an orange point, which happens between 3.1 and 4, and so that would be your end point. Litmus, as we commonly teach, is red in acidic solution, blue in basic solution, and you see a decently large 4.7 to 8.2 pH range over which that happens. It's going to be kind of purple in the middle, and so it gives you a good either or. If something's significantly acidic, it turns red. If it's significantly basic, it'll turn blue. That's commonly put on a paper for just common either or tests. The purple litmus has usually been pH ranged to somewhere in that pH 4.7 to 8.2. Phenolphthalein is far and away the most commonly used indicator, particularly in general chemistry class anyway, where if it's in an acidic solution it's going to be colorless, and a basic range they say it turns red, but really it's more of a purplish pinkish color in basic solution. It's faint pink near the end point, where if you get the pH to about 8.3 it's a faint pink. By 10 it's more of a purple pink color, particularly if you overshoot the titration. But that's commonly used for an acid-base titration, and that works out quite well, particularly for people that are colorblind, because you can see colorless go to pink to a red color where you might not be able to see the color precisely if you're colorblind. You can definitely see it going from no color to a color. And so that's really common. So let's look at these strong acid, strong base titration curves. No equilibria here. We're just talking about strong acid with a strong base. So we can graph the pH versus the volume of the acid, and that's going to be our titration curve. For example, let's consider titration of 100 milliliters of 0.1 molar perchloric acid with 0.1 molar potassium hydroxide. In this case, we'll plot the pH of the mixture versus the milliliter of the potassium hydroxide we add. Note that this is a 1-to-1 mole ratio of reaction, so after 100 milliliters of potassium hydroxide, we will have reached the equivalence point. So here's our basic reaction: perchloric acid, aqueous solution, plus potassium hydroxide forming water and potassium perchlorate. So let's look at the beginning of the titration before we add any KOH. We just got a solution of perchloric acid, so let's just figure out what the pH of that solution of perchloric acid is. Since that's a strong acid, it's just going to be the negative log of the concentration of the acid, because we're assuming 100% dissociation of the acid in solution. So negative log of 0.1 molar is going to give us a pH of 1 to begin with. Somewhere in the middle, after we've added some amount of potassium hydroxide, but before the equivalence point, so we'll pick 20. We said we needed 100 to get to the equivalence point. This is 20, so it's somewhere in the middle. We have to figure out the neutralization, so let's calculate the initial moles of each. We got 0.1 liters of perchloric acid, which was our 100 milliliters, times 0.1 moles per liter, becoming 0.0100 moles of perchloric acid. And then the moles of potassium hydroxide added is going to be 0.02 liters times 0.1 molar potassium hydroxide, giving us 0.002 moles of KOH, where I've added some zeros for precision and significant figures to all those numbers, and you can note the precision. Not all of the acid is neutralized, but some of it, so we need to figure out how much is left. Since it's 1-to-1 stoichiometry, I can just directly subtract the numbers. And so we got 0.01 moles of perchloric acid minus the 0.002 moles of potassium hydroxide, because it's a straight neutralization. We're left with 0.0080 moles of perchloric acid. So the concentration is 0.0080 moles divided by the new volume, so 0.1 liters plus 0.02 liters is going to be 0.12 liters. So that's our total volume. That gives us a concentration of perchloric acid remaining of 0.067 once you do the math. So now we need the pH. pH is going to be negative log of the concentration of the acid again. That gives us a pH of 1.18. So somewhat of an increase in the pH, but not dramatic, certainly. At the equivalence point, that's after we've added 100 milliliters of KOH, so we've completely neutralized the acid. So same calculation as before, 0.1 liters times 0.1 molar perchloric acid, 0.01 moles of perchloric acid, and we've added the same amount, 0.1 liters times 0.1 moles per liter of potassium hydroxide. So we also have 0.01 moles of KOH. Subtracting, because we have a 1-to-1 mole ratio. We don't have any perchloric acid left. We've completely neutralized the KOH. So all we have there is the neutral salt of potassium chlorate, and since it's a strong acid, strong base, they cancel completely. The salt's neutral, therefore the solution is neutral. So we should have a pH of 7 at the equivalence point, as one may think. If you went on past the equivalence point, it's determined by the amount of potassium hydroxide in excess, because I've neutralized all the acid, but we still have a dilution effect going on as well. So let's say I added 150 milliliters of potassium hydroxide. The initial moles is still 0.01 moles, but now we've got 0.15 liters times 0.1 molar, or 0.015. Now we subtract and we find we have a 0.0050 mole excess of potassium hydroxide, which is a strong base. Calculate our new concentration, 0.005 moles divided by 0.250 liters, so that's the 0.1 plus 0.15 liters for everything we added, giving us a concentration of 0.020 molar. We can get a pOH by taking negative log of the hydroxide ion, since that's what's in excess. So negative log of 0.02 molar, it gives us 1.70. Subtracting for 14, that would give us a pH of 12.30. And so that would be a point in the alkaline range if we went past the equivalence point. This is a basic titration curve of a strong acid versus a strong base. Notice here the equivalence point, as we mentioned, occurs at 100 milliliters and is precisely 7 in this case. But notice it's a little S-shaped curve, and the equivalence point is that point of inflection there in the middle where the curvature of the function changes. So what if we did a weak acid with a strong base? And that titration, so we'll do the same problem as before, except we'll change to a weak acid, acetic acid, still titrating with 0.1 molar potassium hydroxide. Again, still 1-to-1 mole ratio on the reaction. So everything's the same except I changed my acid to a weak acid. So we're going to react acetic acid with potassium hydroxide to form water and potassium acetate. At the beginning, we want to calculate the pH before I add any potassium hydroxide to the acetic acid. Since acetic acid is a weak acid, the calculation is going to be based on the equilibrium of acetic acid. So acetic acid plus water is going to form the acetate ion and the hydronium ion, and note that's an equilibrium. So what we'll find is that if we start with 0.1 molar acetic acid with nothing on either the product side initially, we're going to lose on the react side, so minus X, and then plus X on the hydronium ion and the acetate ion. And so at equilibrium we'll get 0.1 minus X for the acetic acid and X for the concentration of the hydronium and the acetate. Very much like our weak acid titration, or weak acid equilibria from the acid-base section of my presentation. Again, go back and review that presentation if you're unsure how this works. So our Ka is going to be the hydronium times the acetate divided by the acetic acid, or when we plug in our x's, we'll get x squared divided by 0.1 minus x, which is equal to 1.8 times 10 to the negative fifth, which is the Ka for acetic acid. Those are values you'll look up in a reference. Typically, there's an appendix in the back of your textbook that'll give you these types of numbers, Kas and Kbs. If we assume x is small because Ka was small compared to the initial concentration like we did in our acid-base section, we're going to make x 0 in the addition and subtraction. So we'll say x squared divided by 0.1 is equal to 1.8 times 10 to the negative fifth. Solve for x. And we find that x is equal to 1.3 times 10 to the negative third molar. Now that x was equal to our hydronium ion, in particular since we're trying to get pH, so negative log of 1.3 times 10 to the negative third molar is 2.9 for a pH. And we find that we're starting at a higher pH than we did with the strong acid case because the weak acids just don't ionize this completely. Now if we pick somewhere in the middle, again after the addition of 20 milliliters of potassium hydroxide, we're going to end up getting a buffer because we're going to form some acetate because the acetic acid is going to react with potassium hydroxide to form potassium acetate and some water. So once I build up enough of the conjugate base to our weak acid, we'll get a buffer solution and we can calculate the pH like we would of any buffer. But we have to figure out the neutralization first. So the number of moles of acetic acid are the same as the strong acid in the previous example. 0.1 liters times 0.1 moles per liter is going to give us 0.01 moles of our weak acid. And we'll have the same number of moles of the KOH as we did in the previous example, 0.002 moles of KOH. We can still subtract just like we did before. 0.01 moles of acetic acid minus 0.002 moles of KOH, giving us 0.008 moles of acetic acid in excess. Since the stoichiometry is 1 to 1, we can just subtract them. Now we can calculate our concentration exactly like we did in the previous example. We get 0.067 moles per liter of acetic acid. But I can't stop there because this is weak. I'm going to need the concentration of the acetate ion as well. The amount of acetate generated is equal to the number of moles of KOH we added, so 0.002 moles divided by that same volume is 0.0167 molar. I need the concentration of the weak acid and its conjugate base before I can calculate the pH of a buffer. Again, the acid concentration works just like in the previous problem. The number of moles of your conjugate base is going to be equal to the number of moles of base you added, because that's straight 1-to-1 neutralization. Taking those concentrations, we're going to plug that into our Henderson-Hasselbalch equation, which again assumes the plus x's and minus x's from your equilibria ice table is negligible. In a buffer, that's especially true because of suppression ionization. So we're going to take 4.7 the pKa because it's negative log of the Ka plus log of 0.002 divided by 0.008. That gives us a pH of 4.1. Remember, the pKa is the negative log of the Ka, so negative log of 1.8 times 10 to the negative fifth is 4.7, or 4.74 if you want to carry it out another decimal place. Now at the equivalence point, we're going to have added 100 milliliters of KOH, same initial moles of acid, but now we're going to have added the same amount of base, 0.1 liters times 0.1 moles per liter is 0.01 moles. And so I'm not going to have any acetic acid left because I've neutralized it all with the potassium hydroxide. And so end up in very much the same position as we did before. 0.01 moles divided by 0.2 liters, 0.005 molar. And that's the concentration of the acetate ion. I didn't have to do this before because the salt from a strong acid, strong base titration was neutral. In this case, I need to know the concentration of that anion. So it's the number of moles of base I added because I totally canceled out the acetic acid, so we're using the 0.01 moles divided by double the volume so we get half the concentration. Since acetic acid is completely neutralized, it becomes an equilibrium involving the acetate ion because the salt that's left from a weak acid, strong base titration is a basic salt. Acetate ion is basic, so we're going to have to work it based on that equilibrium. So we've got acetate ion reacting with water to form acetic acid and hydroxide ion. And we're going to work that equilibrium to figure out the pH at the equivalence point. So 0.05 molar minus X will give us 0.05 molar minus X. And then no product concentration, so we're add X and get X. Very similar to the equilibrium work before. We also need the Kb for the acetate ions. Remember, Ka times Kb equals Kw. So Kb equals Kw divided by Ka, or 1 times 10 to the negative 14th, divided by 1.8 times 10 to the negative 5th, or 5.6 times 10 to the negative 10th. Now we just solve it. Kb is equal to hydroxide times acetic acid divided by acetate, or x squared divided by 0.05 minus x equals our Kb 5.6 times 10 to the negative 10th. Again, that we're going to get rid of minus x by assuming it's negligible, and say x squared divided by 0.05 equals 5.6 times 10 to the negative 10th. Solve for x, and we're going to find out the hydroxide is equal to the x, which is 5.3 times 10 to the negative 6 molar. Take the negative log of that, we'll get the pOH, so negative log of 5.3 times 10 to the negative 6 is 5.3. Subtracting from 14, we get a pH of 8.7. So you note that the pH of a weak acid strong base titration is definitely above 7. If we went after the equivalence point, the pH is determined by the amount of potassium hydroxide in excess, so it reverts to the strong acid, strong base type case at this point. If we add the same 150 milliliters, we're going to still have the same amount of acid, but we're going to neutralize it with excess base, just like in the previous version after the equivalence point. We're going to find that we have excess base, but that's going to suppress the ionization of the acetate ion, so it's not going to really impact the pH here. We can assume that ionization is negligible, so we're still going to calculate it based on the strong base, just like we did before, at 0.02 moles per liter of potassium hydroxide in excess. Negative log of that gives us again a pOH of 1.70. Subtracting, we'll get 12.30 for a pH, which is the same as the strong acid, strong base case. And so we get a slightly different looking curve where we've got the equivalence point, and you can see it's definitely above 7. If we were to flip this around and we used a weak base with a strong acid, the equivalence point would be a bit below 7 because that salt would be acidic, as we covered in the salt section if you look back at that presentation. There's a bit of buffering there in the middle, which is why we have to use a buffer type calculation to calculate the pH there. Now the pKa can be determined from this type of curve at the half equivalence point. So in this case, since the equivalence point in the titration was 100 milliliters, then the half equivalence point is 50 milliliters. We're not talking about the pH at the equivalence point, we're talking about the volume it took to get to the equivalence point. And so we have to half the volume, not half the pH, but half the volume. So if we look back at the titration curve, half of that volume would be 50, and so I've drawn lines there to the x and the y-axis from that point. So at 50 milliliters, the pH at that half equivalence point is 4.74, which is the pKa of acetic acid. This has been a brief tutorial on titration curves.